The next thing we're going to talk about is 3D MEMS process on chip. We talked about bulk micromachining. We talked about surface micromachining. 3D may involve assembly, may involve other kinds of uh, very creative fabrication process. Here is the outline of our Introduction to MEMS series. We are now talking about the last topic for the processing, which is a deeper dive into the MEMS process toolbox. There are a lot of new materials and processes, including inorganic materials and organic materials. Organic materials such as silicone elastomer, elastic polymer, CVD of plastic films such as Parylene, electroactive polymers, inorganic materials such as silicon carbide, silicon germanium, diamond, novel processes like laser micromachining, deep reactive ion etching, focus ion beam etching, chemical mechanical polishing, permanent magnet plating, and rapid prototyping. All this 3D additive and many new materials can be considered. This makes MEMS process rather rich, but it also makes it rather risky for a R&D project. Here are some high aspect ratio devices made of metal. You can use SU8, for example, to pattern very deep structures and then electroplate. Or you can use a radiation process such as LIGA, lithography, galvanoforming, and appforming. And this can be used to create high aspect ratio 3D mechanical structures. We can use nano fabrication processes to make very fine nanostructures, very sharp tips, three-dimensional stacked lattices, or 3D stacked metallic structures. A company called Form Factor invented a process using metal wires formed by wire bonding wires. And this have tips made by inverted molding out of bulk micromachine cavities. And this is later bonded to metal bonding pads to form this 3D arrays of springs that can be used to test the wafers after the fabrication, but before they're dicing. So this is called the ATE probes, atomic testing equipment, ATE market. Focus ion beam etching is another type of process where it's like ion beam formed in scanning electron microscope. You can use this to carve out cross-section structures or break structures such as metal wires, or use growths to form very sharp needles out of carbon conductive materials. The focus ion beam etching can be used to also etch sideways. For example, in this case, you can form capacitors that can measure the displacement of a proof mass that are suspended by two beams. Now, one of the things that's very impressive about MEMS is that people keep on inventing new impossible processes that no one thought was possible. One of the such magic process is called DRE, deep reactive ion etching. The invention of DRE by Bosch makes a name. People typically call it by the nickname Bosch process. This is accredited to two engineers at Bosch in 1996. They invented a method where you can etch very deep structures with high aspect ratio. The process involves etching, plasma etching, followed by plasma deposition, and followed by plasma etching again. The etching is preferential on surfaces that are facing the plasma. So using this step, you can form very deep structures in silicon. The etching speed can be very high. And without this process, people would not be able to make highly sculptured structures like this in silicon. And such, this kind of structures is very critical for inertial sensors such as accelerometers, gyroscopes, and so on. And one can combine such DRE process. It's not just useful for MEMS, but it's also useful for IC. For example, you can use a DRE process to etch trenches in silicon with very narrow defined geometries, grow thermal oxide, and then grow CVD oxide, uh, use CMP to pattern the oxide and then remove of the protective nitride. Uh, Now, how to etch the nitride away without attacking the oxide? That's not an easy process. I'm not going to discuss all the details here, but I hope that this illustrates the connection between MEMS and IC in the sense that a lot of tools that were originally developed for MEMS actually found much, much wider use in integrated circuits. Another type of processing is called electroplating. In electroplating, you put a wafer with a mold. The mold is typically a mask resist layer into a plating bath. There is a layer of seed metal, seed layer, that is connected to the electrodes. And for example, you can have a source counter electrode on the other side. And once the electric current is on, it will pull materials off this source and deposit it into the gaps in between the photoresist. And then you can remove the photoresist. The electroplating process is very useful. A company called Novalis, which is later on uh, merged or acquired by Lam Research, they developed a process where they can plate in very deep structures without forming mushrooms or voids. And this is another magical process. Without this, today's 3D packaging and all this CoWoS metal vias or interposers used in the chiplet packaging cannot be done. Now, when you don't use any CMP process, then when you deposit different layers, they follow the topology of the previous layer, and you end up having something like this. But if you can afford to do CMP polishing at every stage, then you can form much more well-defined structures. This may not seem that important, but on a planar surface on top, you can use high-resolution lithography, and whereas here you cannot because of the focal depth changes. Welcome back to the introduction of MEMS. We'll be talking about MEMS wet processing. If ever you see a slanted structure like this in silicon, it's made by wet etching. This is the outline of the entire series. Um, we're at the end of discussing the MEMS process. Silicon is a crystal structure. The silicon wafer that we use have a crystal structure. Typically, a 100 surface is exposed on the front. There are 100 surfaces like this and 111 surface intercepting the XYZ equally, and then 110, which intercept X and Y equally. Wet etching can happen in 3 different ways. If you have a silicon with a mask, you can have anisotropic etching where the etch rate in different crystal plane is different. You can have anisotropic etching that's vertical, or you can have isotropic etching where the etch rate in different uh, orientations are the same. Wet silicon etch is typically conducted in reflux chemical baths like this. A typical reflux system is a glass jar where wafers are placed inside with good circulation. There is a cooled top on top so that the evaporated liquid would drain back into the solution in order not to change the concentration of the solution. You can use EDP or you can use KOH, potassium hydroxide or ethylene diamine paracatical. The etch rate is different in different orientations. In the 101 direction, the etch rate is the slowest. This is a wagon wheel structure that demonstrates the etch rate differences in different orientations. 111 is the slowest. Uh, as I mentioned, you can use EDP or KOH. It used to be that a lot of people use EDP because the etch rate ratio is very high. But nowadays, people have started to use KOH almost predominantly because EDP is an organic solution that have a very strong smell. So it might be difficult to dispose of environmentally. Now, if you have a 3D structure like this, where the masks are aligned to 110, you are going to form an inverted cavity. The inverted cavity are bound by 4 111 planes. And if you look at the cross section, the slanting degree is 54.7 degrees. The idealized case, of course, is when the etch rate in 111 is exactly 0 or is completely negligible. Then you have 0 undercut. The etch rate is 0 at 111, and the cavity would be bound after forming the inverted pyramid. It will no longer grow any further. That structure is what we call a self-limiting stable profile, SLSP. It's limiting by itself and it's stable. It doesn't matter how long you etch it. Ideally, this is good because in processing you can do over etching and it's not sensitive. You can have transitional profiles that are either unstable or stable. The unstable structures that are transitional changes very rapidly. It's not a good situation if you want to have a high yield process. Depending on the combination of the width of the window and the depths, you can have cavities that look like this, or you can leave a little bit of a silicon at the back. You can have a full inverted pyramid. If the window is very small, then the size of the cavity would be very small as well. Here's one um, example process where you can use this to make a pressure sensor. You have a silicon substrate, grow oxide on both sides. Use photoresist to pattern the oxide on one side. Oxide is a good resistant to the KOH or EDP etching. And as long as the etching does not completely consume the oxide, you can form a deep enough cavity. Here you don't want to form an inverted pyramid, but you want this to be wide enough that you have a membrane. The membrane depth can be controlled in theory. And after that, you can deposit, for example, polycrystal silicon on the front side, or, or you might be able to use doping of a piezo resistor. In either case, this is good for making a pressure sensor. Now, however, this is not a very high yield or robust process. What we mean by a robust process? A robust process is one that is not sensitive to over etch or timing error. If you have a process where the result is very much uh, determined by the timing, then you don't have a robust process. In this case, if the etch rate is fixed and you etch a little bit further, then the membrane thickness would change. And that would be not ideal for a pressure sensor device. So only use this as an example. Now, in reality, the etch rate in 111 is not completely zero. So what happens is if you have the mask and the edges oriented to 110, when you etch it very short amount of time, then the 111 would be intercepting the mask. But as you keep going further, the 111 starts to have an undercut, and you can actually calculate the amount of the undercut by figuring out the etch rate in the 111 direction. Using this inverted cavity trick, you can create a lot of interesting structures, such as this cavity with a grid on top, or this one, um, or something like this. Here you can actually see that the cavity has an undercut because this edge appears to be white. It's white because the scanning electron microscope uh, produces electrons that charges the mask, which is non-conductive. Here we have piezo resistors on this side. Or you can create free beams. This is fixed free beams. So this is a very interesting trick. Welcome back to Introduction of MEMS. We will be talking about gas phase etch of silicon. In the extreme case, silicon can be used as a sacrificial layer material. The gases that can etch silicon relatively fast are bromine trifluoride and xenon difluoride. Those two etches silicon without attacking photoresist, silicon oxide, silicon nitride, aluminum, chrome, and titanium nitride. So it is a fairly good material. The only thing that you have to be aware is that you require a special etching chamber because the bromine trifluoride and xenon difluoride, when they react with any moisture in the air, they would form highly concentrated hydrofluoric acid. So it is very important to be safe. Here is a cantilever being etched by a bromine trifluoride after 30 minutes. And then this is after 60 microns of etch. The cantilever is free. You can see that the undercut is quite significant.